Okay, I think it's fine now. Sometimes if you have something to alert me, you just turn on your mic and speak, because sometimes I don't actually keep an eye all the time on the chat box, so I might actually miss your message. Okay. All right. Okay. So principal component analysis. All right. So this is actually not considered a statistical method because there are no elements of randomness that's built into the method, right? It basically is just a fundamentally a linear algebra method, all right? Which basically is kind of like making rotations of the original space, right? It's basically just making rearrangement, a kind of rotation of your original space, so that you can view the data points in this space from a different perspective. And that different perspective may be actually more useful, okay? So first I want you to get some clear idea, conceptual idea. At least once you understand this method, you should be able to explain it conceptually, yeah? Even without the math. So I'm going to give you an example here. Suppose you have two types of objects, right? So one is you put as plus, the others are circles, right? Okay. Now, if you are here, right? If your eye is here, that's your eye, right? If you see this, if you view the objects at this particular position, let me see. Draw a line. So the objects appear to you like this. Okay. The objects, they appear to you in a straight line like this, right? So do you think you will be able to see that there are actually two clusters in this space?
No. No.
You can't, right? Because the plus and the circles, they are kind of like obscuring each other. So if you think of this as a plane, right? So they're all projecting themselves onto this plane. So what you're going to see is that you're just going to see something like this. So you're going to see the dot here, the plus is here, the dot is here, the plus is here. So they're kind of like, so you make projections, right, onto this plane. So you're going to see that they are all mixed up together, right, on this plane. So this is, in this original direction, is not the best way to detect the presence of these two clusters, all right? Now, if you slightly change your position, let's say now you rotate yourself. Okay, you go here. Okay, you rotate yourself by a certain angle. You come here, right? So you will actually, so the data points will appear to you in, well, actually, let me, so this should be okay, right? Like this. Okay, so data points are appearing to you like this. Okay, so they're all like coming up in the same, at the same angle like this. Okay, slightly longer. Okay. Now, so then they kind of like fall onto they will fall into some kind of so if you then put a perpendicular axis, so let's make a, well, is this perpendicular? Can I rotate this? I can rotate it a bit. Make kind of like 90 degrees, so it should be something like this maybe. Okay, that's 90 degrees, right? Okay, so then what happens is that when you view the data points, they are going to appear like, okay, maybe better, right? Okay, okay, maybe this is not such a good example. So maybe I move myself maybe here. Okay, maybe this direction. All right. So the data points are going to come to you like this. Oops. Okay. Something like this. Okay. Something like this. Okay. So then if you have a perpendicular plane like this, so let's adjust it a bit. Trying to make it 90 degrees. Okay, something like this, right? 90 degrees. Then what happens is that, so this data point will appear here. They all get projected here, right? Okay, so you imagine that there's a line that projects here. So the plus will, some of them, they will project here. Okay, so project. But then of course, some of these will still project here, right? Okay, they'll project here. Now compared to the previous one, right? Now the situation is better, right? You can see some kind of difference between the circles and the plus, right? Okay, after you adjust your position, yeah, from the original position to this position, right? You can now pick up some of the differences that are apparent in the data. So then I want to ask you one question. So how should you rotate yourself so that you can see the maximum separation between the two clusters of data? How should you rotate yourself?
Into the middle of the two data set. I mean, like, I can control this.
Okay. So yeah, so you rotate yourself gradually until you are what's this? How come there's a green line? Okay, never mind. You can rotate yourself until you come to this direction. Okay, from this direction, then the data points will appear to you like this, right? Okay, so this is your plane. So your plane, so a perpendicular plane to those to that direction will be here, this plane. And now you can see that very clearly that the data points are all falling here. Okay, they fall here, and these guys fall here. Okay, so you basically achieve a kind of angle where you can actually see the data in where the separation is the highest. And in fact, what you also manage to achieve is that instead of actually needing two dimensions, right? So look at this data here. In order to see the clustering, right? In the original space, you actually need two dimensions. One dimension here, one dimension here, right? Then you see the cluster. With this rotation, right? After you rotate to the correct direction, you only need one dimension because after you rotate, you make the projection, yeah? So you only need this particular axis, and you can see the variation in the data very clearly. So in fact, you have already moved down from a two-dimensional space to one-dimensional space to look at the variation in the data. Okay, so you have actually removed one dimension, and it's not necessary to represent the data. All right. So this is the basic idea of principal component analysis using an example of 2 dimensions. All right. And then the question is the following. So we will need to figure out how to construct this rotation. Yeah. Okay. The basic idea is like this, but how do we actually do that? Yeah. So just to give you another illustration. So if I have a data, that is like this, let me just draw out the axis. Okay. So let's look at the data. So let's say, suppose this is just unlabeled data, yeah? Unlabeled data, which is like this. Okay. So then you have, if you put a regression line, yeah? If you find a regression line that goes through the data like this, okay? You can actually, well, maybe you just think of it as a linear line, okay? There are many possible ways to construct this linear line. You can put it like this, you can put it like maybe something like this as well, but usually we will put it in such a way that it satisfies certain kind of optimization criteria, okay? So maybe at this point, you can think of it as just a regression line, yeah? So once you put a regression line like this, so of course you will have an equation for it, right? You can write out an equation for the regression line, okay, which is let me see. So this is something like you maybe have something like y is equal to a plus bx. Okay. Your y, this is your x. All right. So then you can also make another line that is perpendicular to this regression line. Okay. So this line has also another equation, yeah. So this line here, let's say this equation would be so this is y equals to a plus bx. So this is y prime equals to a prime plus b prime x, right? It's a different axis, right? It's a different kind of value. So a different coefficients here, okay? So you can think of this axis, so you can think of this filter line as an axis, okay? This is axis y, this is axis y prime. Then what happens is that you make a rotation. You rotate this so that this line now becomes horizontal, okay? So then what happens is that you are going to get this thing here. One line like this, one line like this. Okay, after you rotate this to the axis here, so you will have your y equals to a plus bx as your x-axis, and y prime equals to a prime plus b prime x as your new y-axis. And the data points here, they will basically just scatter like this, right? You think of it as just a rotation, yeah? All right. So then you ask yourself, right? So do you still need to have, so you see that most of the variation, right, occurring on this side, right? So the spread is on this side. Whereas the spread, the vertical spread is actually very little, small. This is large. Okay. So if you want a compact representation of your data, you can actually sacrifice the y-axis. If you sacrifice the y prime axis here, right? This axis. If you sacrifice that axis, then you only have one dimension of data, and you can actually summarize the data. So once you sacrifice this axis, these points will all collapse to this axis. Okay. they just collapse here. Once they will collapse that, it just becomes, you can summarize them using a histogram, maybe. Okay. So instead of needing a two-dimensional representation, you can actually, it will be sufficient to just use one dimension, okay? By making the correct rotation and then sacrificing the dimension that is not contributing much to the variation, okay? So in principal component, there's this idea of trade-off, okay? From high dimensional data, we bring down to low dimension, okay? So this is the gain, right? This is your gain, right? Because the data is easier to understand by a human being at low dimension, right? So you gain this, but what will you lose? You will lose some information. Because when you throw away this kind of access, right, you will definitely throw away some information. But as long as this amount of information is not a lot, right, it should be okay. Right? In order to gain certain things, you have to give up some things. Right? This is actually a principle that seems to be the law of nature. Yeah, if you want to gain something, you have to give up something. Okay, there's no situation where you win everything. All right, it's just whether how much you want to tolerate. Yeah, okay, how much are you willing to lose for certain gains that you wish to have. Right, like for example, if you want to maybe become maybe more proficient in certain aspects of learning, then you might have to wake up, like, you know, when people are still sleeping, you might have to wake up and do some studying, right? Otherwise, well, it just doesn't work, right? Okay, so this is the basic idea of, at least this is a conceptual understanding of principal component analysis. It basically is just involving finding the correct rotation, right? So that the so in a nutshell, right? It basically is just the following. You just want to find, if you are going to just summarize principal component analysis in one word, it's basically just to find the correct rotation. Okay. Actually, this is a linear transformation. Yeah, the rotation involved is a linear transformation. That maximizes the patterns of variation in the data. In the layman's term, yeah. Okay, so the whole idea is finding this new rotations, right? And then you can use this new rotations as your new variables instead of the old variables. Okay. So with that, this is basically a conceptual understanding. Then we can actually move on to the more technical aspect, which is trying to figure out how this kind of thing is actually done. Yeah. Okay, so I have some questions. In Chun, to do PCA, is it necessary to make the data uncorrelated? No. In fact, the PCA can actually compress your correlated data into uncorrelated variables. Like for example, let me clear the board. For example, you may have some variables, x1, x2, x3, x4, and maybe this is your samples, yeah? Okay. So, so they come in all sorts of patterns of correlation. Maybe this one is correlated with 2 1 is correlated with 3, 2 is correlated with 3 as well. 4 is not, or 4 is very weakly correlated with 1, 2, and 3. Okay, so it doesn't matter. So once you do PCA, right, you will get something like this. You will have the first principal component, second, third, and fourth. Okay, if you have 4 variables, you also get 4 principal components. And all these principal components, they are a linear combination of your 4 variables here. Okay, the important part about principal component is that your PC1, PC2, and all that are pairwise uncorrelated. Okay, so your PC1 is not correlated with PC2 and not correlated with PC3 and not correlated with PC4. Therefore, there is no redundant information. Okay, there is no redundant information contained in your PC1, 2, 3. Okay, so this makes it a very good tool to summarize your data, because for your original data, right, your variables may be correlated with one another, so it makes them redundant, you see, right? So that means you can actually, when a lot of your variables are correlated, then principal component analysis will be quite useful for compressing the data. Okay, and lower the dimension of the data. Okay, so to do the PCA there's no need to do anything to make the data uncorrelated. In fact, by doing principal component analysis, you make the data, well, you don't actually make the data uncorrelated. You transform the data so that in the newly transformed variables, they are uncorrelated with each other. Okay. Now let me clear this. Okay. So how is it done? Okay. So I need to talk about some math. Specifically, I need to talk about some linear algebra. Okay. So the raw material. So what is the input, right? The input for PCA is a data matrix, right? So your data matrix X, big X, is like this. So it can be n times p, yeah, right? N rows times p columns. So you have 1, 2, 3. So these are your samples, and this one is your dimension 1, 2, 3, 4, p. Okay, so these are your variables, yeah. Your x1, x2, x3, x4, and xp, right? Okay. So this is so the one that I'm talking about here is this is what we call a R mode PCA. R mode for normal. There's another kind of PCA that is called a Q mode. We'll talk about that later because it's just a kind of a different situation. Q mode PCA. So I'm not sure what Q actually represents, yeah. But the terminology is like that. In Q mode PCA, in your R mode PCA, your N is usually larger than your P, right? You have more rows than variables. In the Q mode, you have the maybe something like this. Okay. Right. In the Q mode, you have many more variables than you have samples. Okay. So we'll first talk about the R mode, right? So in your input is basically a data matrix which has n rows and p columns, right? Now the information, right? The information in X, okay, between the variables is contained in the covariance matrix. Okay, so the covariance matrix, I write it as S. So it's a P times, it's a square matrix, P times P matrix, whereby this is your, these are your variables, yeah? It's a square matrix. Okay, and the diagonal here, right? They represent the. This is actually, of course, since you're doing this for the sample, so it's actually a sample covariance, right? Because you're working on data, so it's a sample. Now, so the diagonal here, they are actually just the variances, right? So x1, x1, they are the same here. So this one is actually, we write like sigma, we put a hat 1, 1. So this will be sigma hat 2, 2 square. Well, I'll just write sigma 2, 2 lah, and so on, right? This is sigma hat pp. So these are actually the sample variances. The sample variance for the variable p. Like for example, for this variable x, the p variable, right? So you'll find the sample variance here. Okay. You'll find the sample variance of the all the numbers here. All right, and so on and so forth. So basically the diagonal here, they are basically just the sample variances, okay, of the columns here. And then the off diagonal, they are basically your covariances, right? So the covariance is like for example, this one will be 1p, right? The covariance between the sample covariance between variable 1 and variable p, okay? So basically in that case, you are looking at, like for example, 1 is here and p, right? You're looking at a pair, okay? You're looking at the covariance, the sample covariance of these two variables, okay? So for those who are, so covariance is basically summarizing how two variables are related to each other, affect each other, okay? So for example, the covariance of two variables x1 and x2 is equal to, it's basically, it's very simple. It's just, you basically construct a, so this one is I, this is 1, I. Okay, so basically this, this is basically a rectangle, yeah? This is basically a rectangle. All right, for example, if you have data points like this, all right? So the mean, right? So this is your x1, this is your x2. So the average of x1 will be maybe somewhere around here, okay? So the average of x2 may be somewhere around here, all right? So this center here is your centroid, right? x1, x2. Okay. Now, so for this, so basically this expression, the I is actually indexing the data points, right? So if you do a line like this, so if you center your data like this, you put a, if you imagine that there's a horizontal line that is cutting through your centroid, yeah? Then you can construct, so these are the rectangles, right? Okay, what are these rectangles? So basically you take the difference between the data point on the x1 direction and subtract it from the x1 coordinate of your centroid. And this one you multiply with the other side, right? So basically it's representing this rectangles. Okay, it's basically representing these rectangles. All right, and the rectangles that are on the first quadrant, right? So this, in this quadrant, so in this is quadrant 1, yeah? So you look at this direction. Quadrant 1, the rectangles are, they all have positive value because both your x values are, your x1 values are greater than the mean and your x2 values are greater than your mean of x2, right? And same with this quadrant. This is quadrant 1, quadrant 2, quadrant 3 and quadrant 4. Okay, so quadrant 3 is also positive, right? Because both of them are negative, right? So they become negative, negative, so positive. Okay, so the rectangles, right, on quadrant 1 and 2 are actually positive. Okay, those rectangles that are on the quadrant 2 and 4, they have a negative sign in front of them because in one of those directions, the difference is negative, right? Like for example, for quadrant 2, the direction on x1 is actually negative, yeah, because you're taking some smaller number than the mean, and you are subtracting, okay? But it doesn't really matter, right? So the positive negative just indicates direction, all right? And therefore, once you understand the geometry, right, things are very simple because, okay, look at this. The data that is like this, right? We know that the data that is like going into direction like this is highly correlated, right? So the covariance is the covariance will be positive. Okay. Why do we know that it's positive? Because based on the geometry itself, we understand it. So the centroid is somewhere around here. And you see that the rectangles, they are mostly on these two quadrants. All right, they're all positive. Okay, so your covariance is basically you're adding them up, you're summing them up, right? Okay. If your data points are on the other side, let's say if your data points are like going like down like this, right? We know that there's a negative correlation, right? And the covariance will be negative. By the way, if you remember, right, your correlation between xy is actually equal to the normalized covariance. Is the covariance of xy normalized by the product of the standard deviation of x and standard deviation of y. Okay, in case you need some refresher. Okay, so the whether your correlation is positive or negative basically depends on the covariance, the sign of the covariance, because your standard deviation is always positive. Okay, so in this case, if you look at the rectangles for the negative covariance, they are basically on these two quadrants, and therefore you will sum them. You are mostly summing negative rectangles. Therefore, your covariance is negative. All right. And if your data is basically more or less like a cloud, right? Is like, let's say you consider the red and the black as your whole data point, then clearly your covariance is more or less zero because your positive rectangles will cancel off with your negative rectangles more or less. Okay, so basically it's just a geometry. All right. Now the covariance is you need to average it, so you divide by. Usually, you can divide by. There are some variants. The usual definition it will be just to divide it by n. Yeah. Okay. Although in some cases they divide by n-1. Dividing by n-1 simply, well, in practice it doesn't make a difference. Okay. If you are more into you want to be like more to academic, so the n is basically when you are dealing with the covariance as a conceptual construct. So the natural way is to just divide it by n, right? Because you're averaging that. People who use n-1, they are thinking of the sample covariance as a kind of an estimator, right? For the population covariance, okay? And because of that, they want to kind of like adjust for biases and things like that. So there's a subtraction, just like your sample standard deviation, yeah? If you talk about it conceptually, you just divide by n. But if you talk about it in estimation sense, you will divide it by n-1. Okay. So anyway, this is the just to give you the background on the covariance. Yeah. So it's basically calculated like this, right? It's basically just a geometry. Yeah. The rectangles you take the sum of the areas of the rectangles, then you average them. Okay, so then you get this covariance matrix, right? So of course the diagonals here would be just the sample variance. So like in this case, this will be just 1i subtract this. Sorry, you don't have 2, you only have 1. Okay. So 1 square and n. Okay. Yeah, so like I said just now, whether you divide by n or n minus 1 depends on the context. Okay. In the conceptual frame, in the original framework where we are not going to be bothered with estimation problems, we'll just use n. Yeah. In fact, n is the intuitive divisor, not n minus 1, right? N minus 1 it is adjusting for some kind of bias in the estimation process. Okay, this is much easier to understand. And in fact, when you work with data mining, you basically you don't bother, because in data mining your n is basically quite large, at least in hundreds or whatever. So when your n is up to 100 already, dividing by 100 or dividing by 99 doesn't make any difference. Okay, so you don't need to kind of like fret over is it n minus 1, this kind of thing. Yeah. Okay. So then okay, so far so I've introduced the 2 things in principal component, which is the data matrix and the covariance matrix. Right. So now I'm going to talk about how to obtain. So of course your covariance matrix is obtained from X, right? In order to find the covariance matrix, you have to work with the data matrix. Okay. So your covariance matrix turns out to be the key in performing the principal component, right? Okay, let me clear this. Okay. Now, okay. So once we have the covariance matrix, we perform something called the eigen decomposition. Decomposition of the of a square matrix. So here your square matrix is your S, the covariance matrix. You don't have to write the P times P. The P times P is just I write it down there to keep ourselves. It's optional, yeah, to remind ourselves that it's a P times P matrix. Okay. Now this is like kind of like a scary word, right? Eigen decomposition. Okay. If you have studied some linear algebra, it might be something that you are familiar with, but maybe that's something in the distant past, right? Because usually this is taught in year 1, and if you don't use it often, then you may actually not recall it too much, right? But anyway, so eigen decomposition is actually some kind of operation that you perform on this matrix here as follows. Yeah, basically it involves solving the following equation: S, and then this is V goes to lambda. So it involves solving this equation. This is your P times P matrix. This is a P times 1 vector. This is actually a vector, yeah. This is actually a scalar. Okay, it's a constant, and this is P times 1. Okay, you know that the matrix multiplication must be conformable, right? Which is if you multiply a matrix with a vector of a vector with a matrix, then the second dimension of the order of multiplication is important. Yeah. Okay, it's not you cannot switch the order of multiplication of a matrix without regarding its dimension. So here P and P must, so the second dimension of the first matrix must be the same as the first dimension of the second matrix, okay? So, and the, once you do this product, so the dimension of the matrix product will be the dimension here for the first dimension and the second dimension, okay? So it will be P times 1, all right? So in order to solve this equation, so you are SV, you move the other side minus V, right? So this is a 0, so this is a 0 vector, yeah? This is actually a vector of zeros. So this is like, again, P times P, P times 1. This is a P times 1 vector. So this is actually a P times 1 vector of zeros, yeah? Right? Which is like 0, 0, 0, 0 P rows, okay? Now, to solve for this, meaning that find lambda and V such that this is true, okay? Right, so the eigendecomposition involves finding two quantities, lambda and also the vector here, such that this equation is satisfied, okay? So this lambda here is called the eigenvalue, and this vector here is called the eigenvector. So an eigenvalue and an eigenvector, they come together as a pair, all right? To get an eigenvector, it's always associated with a particular eigenvalue, all right? So this eigenvalue is basically in principal component. It will play the role of your coefficients of, sorry, not this one. So in principal component, your rotation is actually given by this eigenvector. This eigenvector will give you the coefficients. So it will give you the vector of coefficients of your principal components. Okay. The eigenvalue is will basically give you the you allow you to calculate something called the proportion of variance. Proportion of variation attributed to a PC. All right. So okay, so these are the in the context of principal component, right? What do they actually mean? So okay, so then technically, how do we solve this equation? To solve this equation, it turns out that there's a way to do it, which is you take the determinant, yeah. Take the determinant. So this part here. Okay, let me just simplify it. So from here, you can simplify it as follows: S minus lambda I. You factorize this part here. When you factorize matrices and vectors in linear algebra, you have to be careful, yeah. Okay, it does you can't kind of like just so like here you cannot just factorize like this, yeah. Because you have to in linear algebra you have to respect the order of multiplication. So the correct way to factorize this left-hand side is doing it like this, because this will be P times P. This is the identity matrix, yeah. The identity matrix is basically a matrix where your diagonal is all 1, your off diagonal 0. Okay. So this is a P times P identity matrix. So this matrix operation subtraction is okay, right? It's conformable. Then your vector P here is P times 1, right? So this is permissible, yeah, because the difference here is still P times P, and the V here is P times 1. And if you do expansion, it's like this. So you have S with V, you multiply, you get this term, minus then So lambda IV, right? This you multiply, you get this, okay? Identity matrix in linear algebra functions like 1 in your ordinary real number system, right? So identity matrix multiplied by some vector will give you the vector itself, right? It plays the role of 1 in linear algebra, okay? So basically this one, after we factorize, okay, it's a bit messy here, so I write it down like this. Okay? So I want to solve this, right? So that means I try to find lambda and v such that this is true. So to do this, I will do the following. I take the determinant. And set it to 0. This is a matrix determinant, yeah? What's a determinant? Okay, if you have a 2 by 2 matrix, so a determinant is an operation like this. If you have a 2 by 2 matrix, A, B, C, D, the determinant, yeah, of this matrix, okay? So these 2 bars here means determinant, yeah, is equal to the cross product. The difference between the 2 cross products is defined as such. Okay. If you have a larger matrix, the determinant is actually slightly more complicated. So on and so forth. Actually, there are 9 terms here. So the determinant here will involve something like this. Here it will be A11 times the determinant of A22, A23, A32, and A33. Then minus A12. So it's like this guy times determinant of this part. Then for this term here, you take the negative and then you cross out like this. Then you times the matrix that's made up of these 2 parts. Okay, so I don't want to go to that detail. It's sufficient to know that there's actually a rule to calculate the determinant, yeah, of these matrices. Okay. It's just a general rule to do that, right? In fact, more or less like that, okay? So we don't want to go too much into the linear algebra. Okay, so to solve this, right, once you get the, find the determinant, so basically you have some equation. You will get some equation, and this equation will involve lambda, okay? And then you set it to 0. All right. Then of course, once you set it to 0, you can solve for lambda. Okay. Right. You solve for lambda, then you can solve for your eigen. Once you know your eigenvalue, you will be able to find your eigenvector. Just note one thing. All right. Let me clear this. So you find lambda, then you can find. So after you find lambda, then V will be known. Okay, but note, V is not unique. Okay, it's not unique. Meaning that your eigenvector, there are many possible solutions for your eigenvector, but usually the solutions they involve like differences in sign. For example, one solution maybe you might get something like this as a solution. Another solution might be like this. You flip the sign. Okay. So the actual values actually are the same, but the sign may actually change. Okay. So this is something that you should note because sometimes when different people, they run principal component analysis, they get different eigenvectors. Then they think like, they get the same coefficient values, but the sign is different. So they think that something error must have happened. No, there's no error that has occurred. Sometimes when you run a data set, it's just arbitrary. So your computer will just decide to use either version. All right. So in some cases, even the same data set, right? You use different R versions to do it, you will get a different eigenvector, but that differs only in the sign. Okay, so that's not an error, yeah. Okay, so basically then for each eigenvalue, you will have an eigenvector. And in PC, so the principal component is defined as such. Principal component 1 is actually equal to, I will say this is a V, so this will be x1, 1, 1 plus V 2, 1, x2 plus V3, 1, x3 plus xp, this is vp1, right? So you have first, so this is the first eigenvalue. So these eigenvalues in principal component, they are arranged in such a way that each one is larger than the other. Okay, the first eigenvalue is the largest one, followed by the second one, third, and fourth, and until the p. The eigenvalue is associated with the amount of variation that is present. The larger is your eigenvalue, the more information, the more variation that it explains. Yeah. So your first principal component, so this is associated with V1. So V1, I will write it as such: V11, V21, and VP1. Yeah. So so the eigenvalue P will be associated with the eigenvector P, which I will write as V1 P, V2P, VPP. Okay. So your PC2 will be equal to V 1, 2, x1 plus V 2, 2, x2 plus V2, sorry, this will be 3, 2, x3 plus V P2, xp. Okay. Sometimes it may be easier to write this in a matrix notation. So this will be basically, you can write it as V1, okay, transpose times X. I write it slightly bolder to indicate a vector. So this transpose means, okay, so V1 is this guy here, right? So if you V1 transpose, it will just interchange the row and the column. So you will get V11, V21, and VP1, right? So it's just interchanging the, so P times 1 will becomes 1 times P after you interchange, right? So you can see that this is 1 times P, and this here, this vector here is P times 1, so you actually get a dimension of 1, yeah? So this is basically just a scalar, okay? You end up 1 times 1, okay? So variable X is basically just the vector X1 until XP, right? So then until like the P, if you got P variables, you will have P principal components, yeah? So V1P x1 times plus V2P x2 plus V3P x3 plus until VPP xP. This is VP transpose X. So this is V2 transpose X, okay, and so on. Okay. So here you can see that your eigenvectors. So this is your eigenvector, right? So the eigenvector basically they tell you the coefficients, all right? And why is this important? Now, if a variable is important in influencing, let's say, this principal component, then its coefficient here will not be something that is small. Okay. For example, in this case, if your x3, for example, is useless, if it's useless in influencing on PC1, then its V31 will be close to 0. Okay, that will allow you to, once you know the, if you, let's say you take the first two principal components, right? You can basically look at the value of your coefficients. The values are sometimes also called loadings. You can use that to actually tell, yeah, which what is the meaning of a particular principal component. Okay, especially in R mode principal component, and that is something that is very useful, yeah, in R mode PCA. Okay, and of course in this in PCA there is actually, I think, a requirement that the all right, there's a requirement that the product of the eigenvectors with itself, with the transpose, is restricted to 1. Yeah, this is just to kind of like normalize it. Okay, so there's this particular property. It doesn't affect your interpretation. It's just something nice to have. Okay, because then you know that all the eigenvectors are normalized. Okay. So then what happens is the following. So your PC1, PC2, PC3 until P, they will, so this is associated with lambda 1, this is associated with lambda 2, and so on, right? I can further check the value of my eigenvalue against the sum. Okay, so I can find lambda 2 sum. Okay, so this will give me the relative contribution of PC1 in explaining the total variation. The total variation in your data set is explained by your total variation in your data set, right? It's actually explained by all your lambdas. Okay. And when you divide it by the sum, right? So this gives a kind of like a proportion interpretation, right? Okay. That's why in principal component analysis, we will usually come across statements like this. Like for example, we will say something like 80% of total variation is explained by PC1. And then 15% is explained by PC2, and so on, right? Now, this is very important. Why? So when you have this kind of proportion that's explained by the principal components, it gives you some kind of, now you can exercise your cutoff kind of criteria, right? So how much you want to sacrifice. So remember, our gain in principal component is the reduced dimension, okay? And the loss is, of course, the amount of information that is lost, all right, by reducing the number of dimensions. But it may be, the trade-off may be okay. So let me come to this part here. Okay, suppose you have something like this. First principal component, second, third, fourth. Suppose you have 10. Okay, if this explains 85% of the total variation, this one may be 10%, this one may be 2%, this one may be 0.5%, and this one may be like 0.01%. Okay. In such a situation, you may actually consider just, instead of having 10 dimensions, right, you may actually just retain these 2 dimensions. Retaining these 2 dimensions allows you to keep 95% of the total variation. You, of course, using, so you have, you get to compress from 10 dimension, you compress to 2 dimension. Okay, this is your gain, right? Instead of 10 dimensions, you now just talk about your data in 2 dimensions. What is your loss? 5% of total variation. Acceptable? Right? So generally, I think this is basically okay. Usually, there's no particular magic number that says like what number of loss is acceptable and all that. It all depends on the problem. Okay, so generally people actually try the first few principal components. If they summarize enough of the variation, they will just leave it at that. Like for example, in other problems, your principal component 1, 2, 3 may have some pattern like this. Maybe you have again 10. Maybe this is 45%. It's 30%. This is 12%. 5%. So on, right? So in this case, you might actually, instead of just using 2, you might want to keep 3. Okay, so keeping 3 will allow you to retain like 87%. All right, of your total variation. But okay, this is just a general guide. Okay, how many principal components that you should keep? It's actually a general guide, and sometimes some principal component that explain a smaller percentage of variation can be actually important for separation. Like for example, in this case here, it may turn out that this principal component is actually more important than the first one. It can happen. So there's actually no general theory for this. It all depends on the particular problem that you have. In a lot of problems, the first 2 principal components are usually enough to show the pattern of variation. But this is not always, it's not a law, okay? It's not a law. In some problems, you may actually want to look at the second and the third, or the second and the fourth, okay? So you have to keep an open mind. And usually when we want to explore patterns of variation here, we will make the Drossman plot, yeah, that we learned before, yeah. The Drossman plot for maybe like the first, maybe like PC1 until PC4. So we will look at that, and then we will decide which ones we want to keep, okay? We don't directly just perform this principal component, and then we just take the first 2, end of story. A lot of people do that. If you look at a lot of published work and even some analysis, people seem to like they do not they may not actually have understood that the pattern of variation may not actually be fully explained by the principal components with the largest amount of variation explained. Not always the case. All right, and they usually will go in a very simplistic way that they will just say, oh, take the first 2 because that will explain the most of the variation. Sometimes it works, sometimes it doesn't work. Okay, so my suggestion to you is to maybe look at the first 4 or 5, right, using a Drossman plot, which is manageable, and then you decide which ones you want to keep. Okay, so that will be the theory for Q mode PCA. All right. Before I go to the R mode PCA. Sorry, I will just talk about R mode. Before I go to the Q mode, is there any part that you would like me to explain, maybe in a clearer way or something?
No, here.
Is it clear enough for you? You can ask questions and for parts where you feel like it's not clear enough. So of course, the other property is that your PC1, PC2, and PCP are pairwise uncorrelated. Okay. You can check the correlation; they will be close to 0. Because so this means that your PC1, 2, 3, and all that, they are actually giving you independent information, yeah, which is nice because there's no redundant information in the different axes. So it will be easy to interpret. Anyone wants to maybe have any further questions?
Hello, doctor. Hello.
Yeah.
Okay, Wing Feng here. So,
Oh, okay, Wing Feng, sorry.
so I have a question. So if we use the PCA to as a, use it for variable selections. Okay. So so it's found that the PC1 and PC2 has the explain most of the variations lah. So do we choose like among the PC1, do we choose like the strongest variable in each PC?
Okay, so you are bringing up a point like this. Let me clear this. You're saying something like this. Okay, so you have PC1. Let's say when you do variable, so you have PC1, PC2, PC3. So let's say suppose you want to use it to do variable selection, is it?
Yes.
So you want to see how it explains. Okay, fine. So maybe like I say, I'll have some example like this. So maybe this one will be -2. This one may be okay. Maybe something like this, right? So you calculated all the PCs, right? So maybe let's say suppose there are just 3 principal components, right? Then based on this, you want to pick. So you calculated the PC 1, 2, 3, and based on the eigen vectors, right? You want to decide which one you want to input, right? X1, X2, and X3, right? You want to kind of like rank them, isn't it? For selection, right? Is that so?
Yes, doctor.
Okay. Yes, you can do that. One way to do it will be like this. For variable 1, right? You can take their absolute. You take the absolute of the loading. So for X1, the absolute of the loading will be so this is your variable X1, X2, X3. You sum the absolute loading. So that will, because if this variable consistently affects all the principal components, then it's probably a variable that is important, right? So you can actually rank it by, how do you know its influence? Its influence on the principal component is indicated by its magnitude, right? So you should use the absolute, yeah, so that the sign doesn't actually come in and disturb. So here it will be 5 plus 2 plus 0.05, so that will be 7.05. This one, it will be, you take the absolute, it will be 0.1 plus 0.1 plus 1.5. That will be 1.7. And this one, you take it, it will be 0.5 plus 1.2 plus 1.5. So this will be 3.2, right? So therefore, if you rank the variables, the importance will be like this. First one, most important. Second one is X3. The third one is X2. And then after you rank this, you may actually, there are several ways to do it. Usually, one way is you rank it. So like this, you can use something called a SQB plot, right? So the moment so how many to take? You basically find, So you arrange this, right? Like for example, this is x1, this is your x3, this is your x2, and so on, right? You'll find a point where there's a sharp change. So this is your sum of loading, the sum of absolute loading. So you find there's a sharp point, there's a change, right? Then you drop all these guys, and you take these guys. Okay, you can use principal component like this for feature selection. Does that answer your question? Okay, so that's one way to use it. Although yeah, although generally it is used for mostly for variable dimensional reduction as a variable reduction dimension reduction tool. But yes, you can apply it also for feature selection in using this manner. I mean, at least this is the method that I know it's reasonable. Okay. Okay, so yeah, okay, so I just have a bit more time, so I'll just quickly talk about the Q mode PCA. Sometimes this is, so you call it Q mode PCA. That's why when you look at some literature when people say they use PCA, they are most of the time they are not very explicit about whether they are using the R mode or the Q mode. Just say they are using PCA. And if you're not familiar, if you're only familiar with the R mode PCA, you can get confused, like why is the PCA that they are describing kind of like different from the PCA that you understand? Okay, so basically your Q mode PCA is something that you do when your N is actually, so your P is larger than your N. Okay, so you have actually more variables than your samples. So you cannot apply the R mode. Okay, the R mode is more like this type. The data is kind of like thin, okay, or at most something close to a square. Okay, not like a flattened in this way. This is kind of like a flattened data. Okay, so so in this case here, right? Here your eigen decomposition is operating on the covariance matrix. It can actually also operate on the correlation matrix. Okay, either one of these will be okay. Okay, because your correlation basically is just a normalized covariance. Okay, but when you have a data like this, right, you can't, the eigen decomposition is not on the covariance or correlation matrix. The eigen decomposition here is occurring on a distance matrix between the samples. So so this is a square matrix, right? So this is a P times P square matrix. In Q mode PCA, the information content is a distance matrix between the samples. So this distance matrix is actually n times n. Okay, it basically is a sample 1, 2, 3 until n. And this distance matrix, right, the diagonal is all 0 because the distance between one sample with itself is 0. There's no distance. And then you want to calculate the distance between 1 to 2, 1 to 3, and 1 to n. The distance function between xi and xj, okay, is basically, you can use the Euclidean distance. So Euclidean distance, basically you will take x1i minus x1j. You find the difference square plus x, so this is variable 1, yeah? Variable 2 of individual 1, variable 2 individual j, and you add everything. until variable p of individual I subtract variable p of individual j, right? You square this, right? Then everything you sum, you take the square root. Right, this is the Euclidean distance. There are other possible distances that you can use. For example, Manhattan distance. The Manhattan distance is basically just the absolute. Okay. There's actually no square root. It's just adding everything. Okay. Okay. And so on and so forth. There are all sorts of different distance measures, but the most common one by far is the Euclidean. So you can calculate the distances here based on the matrix, the data matrix X, right? Once you have the distance matrix, your eigen decomposition is applied on the distance matrix. So you will have, because you have n times n, right? So your principal component, you have PC1, PC2 until PCn. Okay, you only have n principal components. All right, and then after that, you basically it's the same. You find how many principal components that you need to take to properly represent the pattern of variation in your data. One of the main difference, so you can still find clustering patterns using QMod PCA, right? By checking the low dimensional plots for the principal components. But there's one main big difference between Q mode and R mode. Q mode. In Q mode, the PCs are not interpretable. In R modes, yes. They usually are interpretable in terms of, that means you can relate the principal components to the variables, right? How certain variables influence the pattern of clustering in your principal component space. Q mode, no such thing. Q mode is going to some very abstract situation already, because you basically have you see, basically you're working with the distance matrix, right? You're not working with the covariance matrix. So the distance matrix already goes to some this space, right, of distances will vary depending on what sort of distance that you use. It could be Euclidean, Manhattan, or whatever. So there's no general theory to properly explain like how the variables actually come in and affect the principal components that you get. Okay, it's different from your R mode, all right? But still, it can be very useful for data mining because sometimes in data mining, you basically just want to work with the principal components. Okay, you are only concerned with prediction. You are not concerned with modeling or explanation. So it's still a doable approach. In fact, in the data, in mining large numbers of, in mining data sets where there are many variables, right? You probably will not be able to apply R mode because simply you have too many variables. And in that case, when you do principal component, you are probably going to work with a Q mode. Okay, and doing Q mode and R mode principal component in R, they have different functions to do it. Okay, later we will look at how to do R mode and Q mode principal component in R. Okay, this Q mode principal component analysis is sometimes known as principal. There's somebody gave it another name, principal coordinates analysis, PCOA. Okay, it basically is just a Q mode PCA. Sometimes people discover these things independently and think that it's something new without checking the theory. Then it becomes kind of like used in applied work a lot, so people don't change it back. Okay, so if you see something called PCOA, basically just a Q mode PCA, right? And people use that because the number of variables is much larger than the samples that you have, right? So basically then people just deal with the distance matrix between the samples rather than use the covariance matrix. Okay. So basically once you understand R mode, Q mode is just a slight variation where instead of working with the covariance or correlation matrix during the eigen decomposition step, you use the distance matrix instead. Okay. And the rest of the things are the same. The eigen values and the eigenvectors pairs, they are the same thing. Okay, with one exception that the principal components are not interpretable in your Q mode. Okay. Right. Okay. So just in time to finish the theory at 7:30. All right. So I think I will just pause here, and we'll come back at 8 with some work examples. Yeah. So I'm going to stop the recording now and resume later. Yeah.
Okay.